we said we need strong materials. So do you remember how do we select our materials, so material designed by mechanical criteria? We had some HB charts. Do you remember HB charts, guys? So we have several HB charts, and for X and Y axis, we have different properties like density. And let's say the Y axis is strength. The unit is megapascal. What's the unit of density? Kilogram per meter cube, right? So it starts from very low density and it can go up to 10 to the 5. Of course, this is log scale. 10 to the 2, 10 to 3, 10 to 4. And we can have very, very low strength materials, or we can have very high strength materials like 10 gigapascal. And in HB chart, you can select different areas designated for example, foams, or like the natural materials, composites. Let's say this is composites, or metals, right? Very high density, high strength. In metals, we also have some high metals like tungsten alloys. Let's say this is tungsten alloy, or some titanium alloy. So we have the categories of the materials, and inside the category, we have specific materials. So, for example, you wanna design a material for space applications. Which area you need to focus on? What are your material requirements?
It should be lightweight.
Lightweight, right? Perfect.
That
so the low density.
Yes, composites could be used.
Low density. So we need firstly requirements, low density, right? And the second requirement in terms of strength is high strength. Therefore, the space material should be in this region, right? This is good materials for example, space application. Perfect. So we have different HB charts. This is just one example of an HB chart. We can have, for example, x-axis could be the yield stress, and y-axis could be fracture toughness. Do you guys remember the unit for fracture toughness? Any good guess?
Something related to joules per meter square. Not right.
It's a good guess. It's not bad guess, but the fracture toughness is kind of related to strength of a material, right? Megapascal, and the length of a per unit length, right? Meters to 1/2. So if your design criteria is yield strength, that means you don't want to go beyond the yield. You can use this kind of HB charts. For example, for high entropy alloys, we have high fracture toughness and high yield strength. For example, for ceramics, this is for ceramics. We have ceramics are strong, but they have low fracture toughness, right? Low fracture toughness. So they are good under compressive loading, but they are not good under tensile loading. Perfect. So having said that, we have different HB charge. This could be also elongation, not fracture toughness, but elongation. And for elongation, like we have, I don't know, let me use different color. Let's say this y-axis is elongation, and we have copper alloys, nickel alloys, copper, nickel, titanium alloys, or I don't know, like high strength steels, high strength. That means in this HB charge, the price paid for the strength is ductility, right? You increase the strength, but you reduce the ductility of a material. And the elongation is kind of related to fracture toughness, but this is another type of HB chart. And here, the price for strength is just ductility. So in this course, we will focus on strength and how we can strengthen our materials. So from material science course, are you guys familiar with any strengthening mechanism? We have main strengthening mechanisms. I'm sure several of you are familiar with some strengthening mechanisms.
Grain size reduction.
Good,
Sorry,
good. Who was it? Is it
was
Ahmet
me.
Hakan?
Yes, hocam.
Perfect, Ahmet. So you said grain size reduction, and the strengthening mechanism is just grain boundary strengthening. Roa, any other example, any other mechanism?
I think the precipitation strengthening.
Great. We have precipitation strengthening. Resul?
Work hardening. Have I said that, hocam?
Great. You guys are doing good today. Work hardening. And the last main mechanism.
Solid solution, hocam.
Solute solution hardening, right? Perfect. Perfect. So the last one is solute solution strengthening. So solute solution strengthening actually the weakest of all. So we will try to investigate each individual strengthening mechanism one by one. We will start with solute solution strengthening, Next, go with precipitation strengthening, then grain boundary and work hardening. So let's start with alloys. So in alloys, we have two different, or let's say more than one element, right? So in the solution, we can have substitutional atoms or interstitial atoms. So what's the difference between substitutional atom and interstitial atom?
Size of the atom hocam.
Size of the atom. So what is substitutional atom?
It is around the same size, and the other one is
Perfect.
smaller.
So let's say we have one solute and solvent. Solvent is the host atom. And we have one host crystal structure, let's say FCC. The size of the solute atom is close to the size of solvent atom. Their atomic radius are pretty much close, right? And solute substitutes the solvent in the crystal lattice without any structural changes. That means if we have an FCC crystal lattice, let me just draw it in 2D. We have FCC crystal lattice. If we have a substitutional atom, they just replace with the host atom. They just substitute the solvent in the crystal lattice. It doesn't change any crystal lattice. How about for interstitial atom? Their atomic radius is much smaller than the host solvent atom, and solute doesn't occupy the sites in the lattice of the solvent, but they resides in the crystallographic pores. That means in FCC, we have different pores, and we call them by tetrahedral sites or octahedral sites. Tetrahedral or octahedral sites. And they occupy in these sites. So they do not change the atom. They cannot occupy at the original lattice, but they can occupy in this T sites or O sites. All right. So this is the knowledge from 218, Introduction to Material Science or Engineering Materials course, whatever. We have another kind of atom, which is called as transformational. So the transformational atom means a completely new lattice is formed by these transformational atoms. They usually occurs as a result of intermetallic compound formation. So completely new crystal lattice. And usually occurs as a result of intermetallic compound formation. Perfect. So the idea of strengthening is always the main mechanism is anything that blocks the movement of dislocation is a strengthening mechanism. So we have one dislocation and any barrier to the dislocation motion is a new strengthening mechanism. So like we have a barrier and dislocation interaction, and this interaction creates new strengthening mechanisms. Actually, the total strengthening, let's call it with tau. It is just the summation of lattice resistance to lattice resistance and these four different strengthening mechanisms, tau additional. And tau additional is just the summation of all individual, we have four strengthening mechanisms, and these are just solute solution, precipitation, grain boundary, and work hardening. For lattice resistance, in FCC, is the lattice resistance high or low? FCC materials, do they have high lattice resistance or low lattice resistance?
Low hocam.
For FCC, it's pretty low, right? That means we have to strengthen the FCC materials with these additional strengthening mechanisms. Okay, we were talking about solute solution. That means we have some solute interaction with dislocation. So solute with dislocations. We have to we have to understand how solutes interact with dislocations. So we have several kind of interactions. First, elastic interactions. Elastic interactions. The second order interactions are modulus interactions. Third kind of interaction, this is third order. It's stacking fault interactions. So they change the distance of Shockley partials. Once they interact with each other, the solute change the distance of Shockley partials. So the distance between Shockley partials are always stacking faults, don't forget. For modulus interaction, the shear or Young's modulus, shear or elastic modulus or Young's modulus will be changed. Of course, elastic interactions are related with stress field. They change the stress field. Of course, we have several, for example, electrical interactions. Or other short range, let's categorize with short range and long range interactions. The solute solution strengthening is dominated by the first type, elastic interactions, and modulus change interactions. So they dominated by type 1 and 2 interactions. Actually, this type 1 and type 2 is also long-range interactions. So what do you understand when I say long-range? Any idea, Roa?
No.
Any idea, guys? Long range, maybe you have good guess.
Hocam, it can be effect in a long time.
That's not a bad guess, but long range basically means that they are relatively insensitive to temperature, and they can be strong up to like very close to the melting point. So long range, let me write long range, insensitive to temperature, and they are strong up to maybe 80% of melting temperature. The other stack and fold interaction, electrical interactions, they are short range, which means that they will contribute strongly to flow stress at low temperatures. Low temperature, let's say, maybe approximately less than 0.3, 30% of melting temperature. Perfect. So the question is, how can we form a solute solution? That was the question that asked from the very early ages. So people came up with copper. They tried to increase the strength of a copper. They tried several elements, aluminum, and they came out with copper is good combination with tin, and they create bronze. They changed the ages, but still they couldn't solve the puzzle, the idea behind the real mechanism, till Hume and Rotary. We have some Hume Rotary rules who solved this puzzle. So he was a methodologist. He studied the alloying of metals in Oxford University. And I think he was the chair of the methodology. And he came up with the rules of solute solution strengthening. Do you have any good guess? How can we create a solute solution strengthening? Like the question is, how can the solute elements can dissolve in metals?
We need to increase the temperature to a very much.
I mean, like in order for gold to dissolve in nickel, for example, what should be the rules? What should be the rules? Actually, like you said it before, for example, the first rule, maybe the first rule. Let me just write rule number 1. Let's say atomic size factor. We state that extensive substitutional solute solution occurs only if the relative difference between the atomic diameters of like the two elements, two spice is less than 15%. If the difference is greater than 15%, the solubility is limited. So the mismatch should be less than 15%. That means the atomic size factor, let's say mismatch, which is just the radius of solute minus the radius of solvent divided by host atom. So we are just normalizing. Times 100 should be less or equal to 15%. Like good example is, of course, copper, tin. This is always a good example. Copper and tin. I think the difference, the size difference is around maybe 5%. Then the rule 1 is valid for copper and tin. What could be this is the first rule. What could be the rule number 2?
Like, do they have to share the same crystal structure? Or...
Perfect. Crystal structure. Basically, the crystal structure of two elements must be identical. Crystal structure. Great. Rule number 3. Any guess?
One should be solute, one should be solvent.
Yeah, exactly. One should be a solute atom and one should be a solvent atom. But the rule should dictate how can the solute can be dissolved in the solvent atom.
Hocam, maybe for the ionic material, the valency of solid atom must be same.
Very good. The valency rule. Who said that? I missed, sorry.
I said, hocam, Enes.
Ahmet Enes, thank you. Very good. Very good. Valency rule says that the solute and solvent atoms should typically have the same valence, like in order to achieve the maximum solubility. Same valence. You guys are doing very good. So can you also help me for the rule number 4? Think about the periodic table. What change if you go from left to right or from top to bottom?
Electronegativity.
Perfect. So the electronegativity rule. By the way, I'm recording this class, right?
Yes, hocam.
So the electronegativity difference close to 0 gives you the maximum solubility. So they should be close to each other. Like what I mean is the more electropositive one element and the more electronegative to the greater is the likelihood that they will form an intermetallic compound instead of a substitutional solid solution. So if one is very electropositive, like if the difference is high difference, they will form one intermetallic compound. You can go ahead and check this intermetallic compound from periodic table. Instead of solute solution. Perfect. So we said we have 4 rules, Hume and lottery, and we have to understand the interaction of solute with dislocation, and we will focus on these two: elastic interaction and modulus interaction. Good. All right, so suppose we have an edge dislocation and script dislocation. So this is edge. We have to find the interaction of edge and script dislocations. And let's say this is script. So do you remember the stress field of edge dislocation, the stress tensor of edge dislocation? Anyone who remembers the stress field of edge dislocation?
So we have compression at the top and tension at the bottom.
Perfect, perfect. We have one compressive stress, like one compressive field. Compressive field. If you go ahead and check the stress tensor of edge dislocation, actually we have covered it before. We have these terms, right? Tension and compressive fields. Good. Tension. How about for script dislocation? Once you check the stress tensor, you will see some shear terms. That means they create shear stress fields around them. Perfect. This is their stress fields, and the shape of stress fields caused by these defects and those around dislocation have significant impact on the strength of a solute. So substitutional solutes, they generally stress the lattice uniformly, and they produce hydrostatic stress fields around the solutes. So let me write it. Substitutional solutes, they create hydrostatic stress fields. And the hydrostatic stress fields, they are relatively weak obstacles. They are weak obstacles to dislocation motion. Dislocation motion. Therefore, they are not strong barriers. That is why this solute solution strengthening is not the best strengthening mechanism. But okay, we start with edge dislocation, and we have screw dislocation. So we will have some solutes here, some solutes here, and their stress field should interact with the stress field of dislocation. Therefore, if we have tension stress fields, they will go ahead and interact with the compressive stress field of dislocation and create additional mechanism. So if we have compressive or tensile stress fields, they cannot interact with screw dislocation, because screw dislocation has shear stress field. We need some shear stress field to interact with dislocation. So let me quickly summarize. In FCC lattice, of course, we always think if the solute is interstitial or substitutional atom. All right. So in FCC, let's first start with substitutional solute. The substitutional solute will create some hydrostatic stress, sigma hydrostatic, and interstitial solute will also create some hydrostatic. Let me not write stress, but I will write strain instead of stress. Hydrostatic strain, because they basically expand the lattice, and this strain will create the stress. Interstitial elements like hydrogen, fluor, nitrogen, they also create hydrostatic strain. BCC, substitutional, they always create hydrostatic. Substitutional atom, they create hydrostatic strain. How about interstitial solids? Interstitial solid. This time, not in BCC, they create shear strain. And you know the stress field of dislocations. Edge creates tension compression, and screw creates shear. So the next question is, what interactions might be expected between solutes and dislocations in different lattices in FCC and BCC. Any good answer? So let's start with FCC. For edge dislocation, can you expect an interaction with edge dislocation with substitutional atom or interstitial atom?
Like we could, hocam, and it would decrease the dislocation mobility.
Perfect. So both solutes, interstitial and substitutional, they create an hydrostatic strain, right? Therefore, we will observe strong interactions with both type of solute. How about screw dislocation? Screw dislocation, it has a shear field, shear stress field or strain field. Can it interact with tension or compression due to hydrostatic strain? So they will create tension compression too. Can we see any interaction?
No, hocam.
Good. So we will see no interaction with both type of solutes, right? So for BCC, edge, let's start with edge. So edge dislocation, what kind of interactions can we observe? Which type of solute can it interact?
Like it's going to interact with substitutional ones, but it is not going to be interacting with the interstitial ones, I guess.
It's a good guess because edge dislocation has tension and compression stress fields. For substitutional atom, they will create some tension compression, right? So they can interact, but interstitial create more shear strain. But the thing is, this component is not asymmetric. This component is not symmetric. This component is asymmetric. Therefore, they can still interact with tension or compression fields. So strong interaction with substitutional atoms and less interaction with interstitial atom. How about screw in BCC? Screw will create shear field and they can interact with shear strain, right? Therefore, they have strong interaction with interstitial solutes. They can have strong interaction with interstitial solutes. So this is very important, the stress fields around the solutes. Is there any question with respect to this one, till this one? Roa, any questions so far?
It's clear for me, Hocam.
Resul, is it good for you? All clear?
Yes, all clear.
Good. Good. So BCC, the interstitials are important elements too. But where can interstitial locate? Where can they form in BCC? So in BCC, I'm sorry about my handwriting, but I will try to draw the BCC lattice. It will not be the best BCC, but I just want to give you the main idea. These are the host elements. Oops. So these are, let's say, lattice sites. Host. That means solvent, right? And in BCC, of course, we will have body-centered cubic, and we will have these connections. We have some octahedral sites. Let me show them by red. These are octahedral sites. So this is octahedral. And we have some tetrahedral sites. Let me show them by blue dots. So these are the tetrahedral sites. Of course, at each phase, you will see these. These are. So how many octahedral sites do we have in BCC crystal lattice? Think about the octahedral sites. So in between these atoms, we will have octahedral sites. And of course, in between these. How many do you think? Can you count the octahedral atoms?
16 hocam, is it?
It is almost 16. Actually, it's 18 octahedral sites and 24 tetrahedral sites we have in BCC lattice. Perfect. Having said that, so we know the mechanism for solute solution strengthening. So let me just summarize. The solute creates an internal stress field due to the size or modulus mismatch, right? Solute creates some stress fields. And this stress field is just due to size or modulus mismatch. Modulus mismatch. And this stress fields, they interact with this location, these locations, and they act as an obstacle to this location motion, and they create an additional hardening mechanism. Perfect. So let's give 10 minutes break and continue after the break. Is there any questions so far?
No, hocam. Thank you.
All right. All right. I'll just pause. Perfect. So let's do some calculations. We will do first size effect calculations, then modulus effect calculations, and we will just superpose them to calculate the total effect of both size and modulus. Basically, we need to find the force, interaction force. The interaction force is just the derivative of interaction energy with respect to any position. Will give you the force. So the interaction force between solute and edge dislocation due to the size mismatch is called para-elastic interactions. So let me write. First, we start with size effect. And the interaction between solute and dislocation due to size mismatch is called para-elastic interactions. And to calculate the interaction energy, it is just pressure times the volume mismatch. Do you guys remember how we can calculate the pressure? It is just the summation of all three stress tensors. Times the volume mismatch. So you guys are familiar with all of these, and you guys know how to calculate this. So after basic calculus, we came up with the result is shear modulus times Berger's vector. We have delta V here divided by 2 pi 1 minus, oh, by the way, we are doing it for edge dislocation. Y x squared plus y squared, which is equal to, again, minus mu b volume mismatch 2 pi 1 minus Poisson's ratio. This is just sine theta, sine gamma divided by r. Interaction energy. And to calculate the force, interaction force, we just need to take the derivative of this interaction energy, partial derivative of interaction energy with respect to the position, right? And it is minus mu b delta V 2 pi 1 minus Poisson's ratio sine theta sine psi divided by r square. All right, so for an edge dislocation in FCC lattice, the maximum force, in order to calculate the maximum force, you just take the derivative of force and equate into 0, and you can find the location. Let me give you the maximum force. It occurs when x is equal to b by 3 and y is equal to b by 3, and r squared is just 9b squared divided by 4, and both angles are equal to 1. That means the maximum force is equal to minus 9 shear modulus, volume mismatch, 8 pi 1 minus Poisson's ratio times the Burger's vector. The only unknown here is the dilatation, right? The excess volume. The dilatation or the excess volume is equal to the lattice parameter A0, 0, we have another constant psi here, cube minus a cube, which is more or less equal to 3 psi a0 cube. And what is psi? Psi is nothing but 1 over a d a0 by the concentration of solute, which is the logarithm of a0 by dc. So I put this into this one and this one into excess volume, and due to size mismatch, the maximum force that occurs between solute and dislocation is just minus 27 mu psi a cube divided by 8 pi 1 minus Poisson's ratio times the Burger's vector, which is more or less equal to mu times b squared times psi. So does this equation looks familiar with you? Is it familiar with you, this equation? Mu b squared. Ra, do you think this one is familiar with you?
No, hocam.
This is actually Frank's rule, right? Mu b squared is the energy of dislocation. This is Frank's rule. So substitution of solid solution strengthening is essentially connected to mu b squared and always relies on the interaction of solute atom with dislocation. Perfect. So this is for size effect. How about for modulus mismatch? Modulus effect. So we said was it this equation? No. solid solution may have different shear modulus than the matrix, right? That is why we have some modulus mismatch. And this is called the elastic effect. So we have the same process with the size effect, and the interaction, elastic interaction, is just minus mu b square 8 pi square r square and another constant times n. And n is nothing but 1 over mu the mu times dc, the concentration, which is just logarithm of this shear modulus with respect to concentration, and the maximum modulus mismatch, the force due to the maximum modulus mismatch is 1 by 20, again, mu b square times n. Again, it's related with mu b square. So the interaction forces are related to dislocation line energies. The paraelastic interaction is only possible for non-screw dislocation segment, and the paraelectric interaction is long range. Let's go back to paraelectric interaction. We should have one over r term here, right? So it is long range, but the dielectric interaction is short range. Here we have 1 over r square. So this is short range. What was the difference between short range and long range, Resul?
The long range one is temperature insensitive hocam, and the short range is dependent on temperature.
Perfect, perfect, great. This is paraelectric and long range. Paraelastic and long range. Perfect. Then we have both, we know both effects. And the pitch collar force, which is just the summation of both effects, just the maximum of paraelectric and the maximum of dielectric and paraelastic, which is equal to the excess stress tau c times b times the distance LF. And this fiddle distance LF can be calculated the obstacle spacing for dislocations on the glide plane. So this is important, guys. Please don't forget, because we will need it for precipitation hardening too. This is Friedel spacing, and LF is nothing but 6 mu divided by tau c b cube 1 by 3. Then F max is equal to minus tau critical 2 by 3, B 2 by 3, and 3 mu divided by C 1 by 3. Perfect. Then we saw that this excess stress is just, let me write, tau C is nothing but, so from this equation, I'm getting this one because we need this one to calculate, because we said total tau is related to the lattice resistance plus all other effects. And we are trying to calculate the solute solution effect. Tau solute solution, you can call it this way, is just F max to the 3/2 square root of C B divided by 3 mu. This is very important. The summation, like the bottom line, is excess stress is proportional with the square root of C. If you increase the concentration, the excess stress is linearly proportional with the square root of C. All right, and the total C is just, we have two different effects, GB square, square root of C. This is very important. We have size effect and modulus effect. 3/2. So this is very important. If you draw the excess stress with respect to square root of C, excess stress due to the solute solution, right? Let's say this is megapascal. 5, 10, 15. And for example, 0.05 and 0.1. This is silicium in copper. We know the excess stress is linearly proportional with square root of C. This is aluminum in copper. And this is tin in copper. And copper plus tin is just bronze, right? So they came up with the best element with copper is tin. And this mismatch, this part, will dictate the slope of this straight line. So this straight line is just the slope, right? Because this equation, if you try to calculate tau C over square root of C, you will get this coefficient. So the slope is nothing but this parameter. Perfect. To sum up, the strengthening due to solute solution is proportional with square root of solute concentration. So any questions so far?
No, hocam.
Perfect. So let's summarize. Solid solution. The obstacle, the nature of obstacle is solutes. This is just a weak hardening mechanism, and the hardening law delta tau due to solute solution is nothing but just proportional with square root of C, G epsilon S, 3/2 square root of C divided by 700, something like this. All right, guys. If you don't have any question, we can call it a day, and I will see you next week.